All right, I don't know if I can do this under 5 minutes, but I'm going to try to do the best I can. And so this is just talking about chapter 13. First, a disclaimer. As I'm wearing my Big Bird shirt, do you remember Sesame Street? Um, I don't know this stuff any more than maybe you might, but I think I'm trying to get grasps on it. And the only way I can get grasps on it is if I talk about it and then maybe try and teach it. So we're going to just review chapter 13 very, very quick, right? Just to get us to a point where I want to talk about, and this is where we're going to hit right here. So I want to talk about the human evolution, all right? So, but first, we're going to skip everything that you do or know all the way up to chapter 13, because if you're watching this, you should know chapter 13. This is what we're covering, right? Nothing else before. All right, so this is the best way I can do it here. And sorry it's in blue, because if you want anything else, you're going to have to kick down, because I seem to lose these all the time when I'm at school and when I'm just running in the classroom doing it. Let's just say that you have alleles here and alleles there, right? And this is an F1 and this is an F1, okay? Now, if there's link disequilibrium, you can see if the alleles vary. If there is no link disequilibrium, you have no idea if there's a variant allele for that or not, because it will never show up, all right? So in order for you to see this, from what I'm gathering in the book, there must be some link disequilibrium, which just means that I believe that these line up in a way that they can be swapped, right? That there can be changes through mutations or whatever, right? And that recombination and all that. And so we're talking sex gametes. And so this happens, right? And then when we get to the F2 generation, if there's differences here, then we should be able to see it. However, this one shows up, okay? And what we're talking here is a phenotypic expression. It's phenotype, right? And so they give an example in the book of Drosophila, and Drosophila with the bristles on the abdomen and the back, whatever, right? How they can select different mutations of that, and then just track that and see how they all work, right? And so that's what they see, right? They can, because there's differences, and they can track the differences and see how they can tell that, that's one change for the evolution of a phenotype. And so this is what chapter 13 is, right? They're explaining kind of the QLT, yes, QTL, which is the quantitative trait loci, right? Please tell me I'm right. Yes, okay. So that's just where these are located, right? And how they interact and what we're gonna see. Less bristles, more bristles, kind of all that. That's kind of what I get. And that all is what? That's a variance, right? It's a variance in what? In a phenotype. And so we already know that VP equals VG plus VE, right? But here's where we expand on VG, because now VG equals VA. And VA, all that is we already know that can be mutations in a gene, and we know genes can affect other genes, right? So we have the epistasis, right? Where one, right, affects the other, or you have the pleiotropy, where one gets a mutation and actually affects two different kind of phenotypic characteristics or trait, and you don't realize that happened, right? But there's one, right, affects many. One affects two, but who knew that was going to happen, right? Because they're so dissimilar. Something, one gene makes a change in my ear size and, creates a different hormone in my liver, right? Go figure. So that's kind of where we're getting to, right? Is the evolution of phenotypic changes. And this is what really gets to it, because we know it's those micro mutations, right? It's a microevolution which, when everything else is stable, causes change within that population, right? Within our population. So, what does that mean? So, the VG equals VA is only the additive variance on a gene. And we know that additive means that we just don't have, dominance or recessive, right? Remember how it came goes? Here's this, right? Here's A1, here's A2, here's A1. I like to do it this way. In the book, they say that. Here's A2, okay? And you have, you have this kind, right? So we're talking about, the additive, right? There's no dominance in it. And so that's VA. And that's pretty cool. Because now we're going to use VA in a series of equations that, show kind of its influence, right? But we already know that VP equals VG plus VE, right? But one that they've got to is actually the hereditary of it. How this all passes down is, and I'm just going to throw this up here real quick. It's H2 equals VA over VP. Yeah, that additive over this, right? And this, right, is all of that together. But what they like to do is take this out and then know the ideal model of that. All right, I hope that's as close as we can get up now. That's just the genetic side of it, but I didn't go through the rest of the equations there because I want to get to this, right? This. All right, here's what I'm going to skip. I'm going to skip the point where if you don't have the VA, right, and you don't have kind of one gene, then the only thing that affects a population is the genetic drift, right? And genetic drift, if everything's stable, will actually work against the individual for this, right? Because you never know what that's going to do, right? If this happens, then it has to it has to outperform that in order to affect the population, okay? Or I could be wrong, right? Look at that. Or I could be wrong, but I don't know. Let's see. Now, let's move past that into directional selection. Not directional selection, but there is a direction for the selections, but this is selection differential, all right? So if they say that there's a population of this, which is just a trait, and within that population there's a mutant, that, right? And here it is. If you select for that, then what? That's selection by differential. That's differential selection. Selection from differentiation, right? Maybe you like that. It kind of looks like it's part of artificial selection, but who knows if that happens out there, right? But here's what's kind of cool. This equation, which I like this equation more than anything else. This equation is the response of this, right? Through, and I'm just gonna write this in, through hereditary, right? And I believe that's H2 because it takes for most species in order to make one of two. Okay, I may be wrong, but I think because why other So this, right, is the number of existence of that. But do you want to see its influence of that? Look, the hereditability of that has to work against this, right? Which is all this presence in the population, right? if this is to take over that and affect it. Unless this leaves, right, and starts its own. Now, this that I drew down here is what is termed its realized heritability, right? Because that's going to be some number there. Or, well, actually it's going to be that, right? That's contribution of one of them. Squared would just be that. But check this out. In the graph they have here on page 355, all right, and this is where I'm kind of get to, is that response due to the selection of the parents to S. You see what I'm saying? Whoever has this has to decide if it's going to mate with this or not, right? Because what if there's another like this it finds in the population? It may choose that just because that. Now, does that happen? Well, of course it happens. It happens all the time, right? In normal populations. You look at someone, you go, ooh, they're very familiar. They have the same habits that I do, right? Oh, well, that's an opposite sex of mine. I wonder if I can mate with it. Oh, look at that. Boom. That could happen, right? And they become this and create that. That's pretty friggin' awesome. Do you know why? Because you can put this kind of model to different predictions about an organism if the environment goes different ways. Nah, I like it. I like it. The real reason I like it is because the chart there for that Homo sapien, right? For the cranial capacity, do you see? What is that? Between 10 to the negative 4, 10 to the negative 3. All right, so I don't know if this is right or not, but obviously, an expanded structure of cranium, I believe, has the room for excess mass, i.e. brain structure. Now, what's really cool about this is if you look at just the heritability of the Phototaxis and Drosophila, I mean, okay, it's a stretch, right? But let's go to just a little extreme. It's like 0.09, right, for the heritability. Now, I don't know what this number would be, okay, for Homo sapiens at the time, because I don't think we would know the actual numbers, right? We wouldn't really know the effectual population, but they had to decide. And this is what's so cool, is there's a chance that this gets passed on if this does this for mating species, right? Or if this does this with a mating species here, right? So you could have this and this. And this we're going to call the bigger brain, right? And we can have it on this side too. Compartment, the bigger brain compartment, right? Or there's a chance that this one can mate with this one, and it doesn't. Now, this may be a family unit. You may get one over there, and this one has a bigger brain, but the offspring doesn't. Capacity. This one could be the same. They could leave the group, right? You get more of this, right? But what happens if that mutation happens again? And what if their offspring becomes this? You see what I'm saying? Now these may migrate out. Especially, look at this, right? Especially if you took this and this one was this and this and this and this. And what if they said, let's get the hell out of here? It's hot, right? And they start walking. It's a stretch. I get it. It's a stretch. But that point, right? How long that whole history of human beings were breeding, and how maybe that just one, maybe, possibly, bullshit, I don't know. But that bigger brain capacity gets passed down to here. And, now turn back to here, right? Turn back here, right? Turn back here to, was it not in here? No, it wasn't. Hold on. All right. Here's this. Boom, 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 boom. Trial one. Boom, 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 boom. Okay. Here. For Drosophila, right? Sperm sizes. Say this is the F1 times F1. And the next one is F2 times F2. And you get F3 times F3, right? And say this is the larger sperm that they bred with each other, and this is the smaller. And then just go on pesticides, right? Look at the migration patterns. Look, here. These are not my migration patterns, but these are how the disproportions increased, right? Over time, over lineages and generations. So you can see it is possible, right? That brain just kept getting bigger, compartment-wise, until it just averages out to what is the balance between how much head a person can hold and how much the function of the body is, right? And it probably wasn't convenient to do this with a big head, and so gradually, they needed to stand erect, develop the vision more and more. Do you see? That's cool. You can just look. And where do we start? QTL. All right, that's as far as I got in chapter 13. I don't know.